Audio? Good. Should have just watched while I was sliding my chair across. That would have told me right then whether I had audio. So, who has questions from the homework assignment? And who has their homework assignment ready to turn in? Oh yeah, we're going to do 23. Yeah, I don't know. We'll look at 36, but we're definitely going to do 23 because that's the interesting one. Well, 3-8 you said? You actually have to back up to the kicked football, 3-6, which is where it starts. But there's something interesting going on here. So let's take it one step at a time as we work through this problem. If you want to follow it in the book, it backs up to example 3-6 about a kicked football, and then the issue with the kicked football is that, as with the water coming out of the nozzle of the hose, you're looking at something that starts at level 0 and ends at level 0. So anytime you have something that's going to undergoing gravitational acceleration, but it's starting and finishing at the same value of y, in this case y equals 0, you have the equation. Is this one already dying on me? Y equals y sub naught plus v sub naught y t minus 1/2 g, which is 4.9 meters per second squared times t squared. Now, in this case, you're starting off, you're finishing, when you're wanting to find out when the water hits the ground. So when does it come back to 0? Well, it starts off at 0. Okay? Now right here, we've got v sub naught y. But we weren't given v sub naught y, we were given v sub naught, right? Which was what? 3.5 meters per second? 2.5 meters away, 6.5 meters per second. And the range it's going, the distance it's going to travel, is 2.5 meters. Well, first thing we want to do is convert v sub naught into, make sure the sign-in sheet makes it back over there for me. First thing we want to do is convert v sub naught into its rectangular components. So we have v sub naught x, which is equal to 6.5 meters per second times the cosine of theta, and v sub naught y, which is 6.5 meters per second times the sine of theta. That's just standard converting your polar form into your rectangular form. So, what we have here is 0, as an equation, we have 0 is equal to v sub naught y, which is 6.5 meters per second. You know what, I'm just going to, instead of keep writing the numbers, I'm just going to put that back as v sub naught, because we know it's just a number. So we have v sub naught times the sine of theta times t minus 4.9 times t squared. Now, some of you may have picked up on this last week or maybe the week before. I lose track of these things. But we looked at one of these quadratic equations where I said there's sometimes it works out that you can just factor it out. This is that time. And it happened because we were starting and ending at the same level, at the same altitude, or the same value of y, which we could then conveniently set to 0. Or, just to make the point, even if we didn't set it at 0, if we said we're starting and ending at y equals 5 meters, then this would just be 5 meters equals 5 meters plus all of this. And we would subtract 5 meters from both sides, and we would still end up with 0 equals this part of the equation. Now look what happens when we factor out a t. This product is equal to 0. There's something special that is true whenever you set a product of two terms equal to 0, or a product of any number of terms. You can multiply as many terms together as you want, but if the product of them all is equal to 0, then that means at least one of those terms has to be 0. Okay? So, in this case, there are two solutions. There is when t is equal to 0, obviously it's 0. That's one solution. Kind of a trivial solution. It means that the ball started at this point at t equals 0 at 0. At the level you're aiming, you're ending at. The other case is when all of this is equal to 0. So when 0 equals v sub naught sine theta minus 4.9 t, that's also a solution to this equation. So we solve it for t and we get, subtract v sub naught sine theta from both sides. We get minus v sub naught sine theta is equal to minus 4.9 t. And which actually I'm going to rewrite that minus 4.9 as g over 2 again. Because remember that's where 4.9 came from up here. It was minus 1/2 g times t squared. So multiply through by 2, you get minus 2 v sub naught sine theta equals g times t equals minus g times t. Divide both sides by minus g and we get 2 v sub naught sine theta divided by g equals t. Okay? That's the first part. Now, what we also want to know is how long is it going to, how far is this thing going to go? We can also write the distance that it's going to travel. It's 2.5 meters is equal to, which is the range that we're solving for. That's going to be equal to the v sub naught x, which is v sub naught times the cosine of theta times time. Distance equals rate times time. This is the horizontal component of its velocity. This is how long it will be in the air. This is how far it will have traveled. Okay? So we can rewrite t as being equal to the range divided by v sub naught cosine theta. Now, we also know that t is equal to 2v sub naught sine theta over g. Everybody with me? Let's just plug all this back into our equation. What do we have? We have 0 equals v sub naught sine theta t minus 4.9 t squared. We've got 2.5 meters equals v sub naught cosine theta times t, where we can rewrite that as v sub 2 times v sub naught squared you know what? Let me make sure you see where this is coming from. V sub naught cosine theta times t, but t is equal to 2v sub naught sine theta over g. Okay? That's our range, our 2.5 meters. From a trigonometric identity, I didn't look. I meant to look. Is this in the back of your book? It is. Look in the back of your book at the bottom left-hand corner of the page. You'll see a trigonometric identity that 2 times sine theta cosine theta is equal to sine 2 theta. So this 2 times sine theta cosine theta is equal to sine of 2 theta. So we can now rewrite this range equation as v sub naught squared over g times sine of 2 theta. In the past, working one of these problems, you would have simply plugged in the initial velocity because it would have been given to you specified as so many meters per second at such and such an angle. In this case, it's the angle that you're having to solve for. Okay. Remember the whole solving simultaneous equations? 2 unknowns, 2 equations. We had to use the equation for one of our components. We had to use the equation for our vertical velocity, our vertical position as a function of time. We also had to use and solve the equation for horizontal position as a function of time. solve that equation for t, put it back into the original equation, we come up with a function with range as a function of theta, of the angle, of our first unknown. That is independent of the time of flight that the water or the football or the cannonball or whatever is going to be in the air. Now, before you break out your calculators and start doing a whole lot more math, look at this. How does it vary? It varies as a function of theta. When will it be at its maximum? When will this value, when will it be the most it can possibly be? What's its maximum possible value? No, 2.5 is the value of a range that we're eventually going to plug in and actually solve for a couple of angles of theta. But right here, you can look at this and see it will be the most it can ever be is when sine 2 theta is equal to 1. Okay, which means when 2 theta is at 90 degrees. That's the largest the range can ever be. But notice, I said when 2 theta is at 90 degrees. That means when theta is half of 90 degrees or 45 degrees, you're going to get your maximum range. You draw the picture. When 2 theta is 90 degrees, theta is 45 degrees, and you're going to get the maximum range. Okay? You will never get a range greater than v sub naught squared over g. You can't, that's the old joke when someone asks for directions and the person says, oh, you can't get there from here. Well, in this case, it's literally true. You can't get there from here unless you increase your initial velocity. But given that velocity and the acceleration of gravity, this is as far away as you can get that cannonball or that football or that water stream to go. But what happens if you decrease this angle? If you decrease the angle, then the water jet is going to start hitting closer and closer to you. If you increase the angle further, the same thing starts happening. So there are going to be, and this is the whole point of the final question, what is it, C? It doesn't label them with letters, but the last thing it asks you is why are there two different angles that will get you the water jet hitting 2.5 meters away? This is why. Because there are two solutions to that equation that will give you 2.5 meters. Well, that's the work, so let's plug in the numbers and get the answer here. We've got 2.5 meters. Oh, here, I can just keep working right here. And we know v sub naught was what, 6.5 meters per second? And g is 9.8 meters per second squared. That's right, we sure do. Thank you. Thank you. I almost lost that. Where did I sure do. Right there. It's V sub naught squared. Now, units weren't working out. But let's make sure that the units work out. We've got meters squared per second squared, divided by meters per second squared. So these cancel one of those, these cancel both of those, and we're left with meters equals meters. Or make sure you sign the sheet. So let's, this also means we're going to end up having to I'm getting ahead of myself here. Let's solve this first of all for theta. We have range times gravity equals V sub naught squared times sine of 2 theta. Divide both sides by V sub naught squared. What am I? Say again? Well, yeah, you take the inverse sine of that and divide by 2, but we should still end up with 2 solutions, which means that I'm skipping something important somewhere. Well, I don't know what I'm skipping, but I can only assume we're going to run into it. So let's take the inverse sine of 2.5 meters per second times 9.8 divided by, what was it, 6.5 squared? What does that equal? That gives us 2 theta equals 35.44. So why should we end up with 2 solutions there? We end up with 35.44 equals 2 theta. But what I want to know is, why are we not coming up with 2 solutions? Go back to your, what is it? Go back to example 3.8. It's on page 63. And you'll find that you solve for the the sine of 2 theta. Right? But remember, I've told all this before, you have to do the math. Keep track of the angles. Keep track of where you are. We solve for the sine of 2 theta. Now, in practice, we're looking for theta that's going to go from 0 to 90 degrees, right? But that means we solve for an angle between 0 and 180 degrees. Does everybody understand that? Let me clear out some space here. Where will I do the least damage? Right. Theta is going to be from 0 to 90. But that means 2 theta is going to be from 0 to 180. Now, in the range from 0 to 180, not range, domain, yeah. In the domain of 0 to 180, how many times will sine equal, what did we come up with? 0.578? How many times will sine equal that? We'll equal it once here. And it will equal it again here. So, we get the first angle of 35.44. When else would it be? When you subtract this from 180. So theta 2 equals 180 minus theta 1. Everybody understand why that's true? Look at the symmetry of your y coordinate, the sine of the angle. It's here. That means this angle is also theta, equal to theta 1 above here. So this becomes 180 minus theta 1. So, in this case, theta 1 is 35.44 divided by 2, which is, somebody with a calculator? 18 degrees. Okay. What is 180 minus 18 degrees? Say again? 162. Yeah, once again. Yeah, I did this too quickly. 2 theta is 35.44. So, what's 180 minus 35.44 would be what? Something like that? Okay, now divide those by 2. $72, and what was the first one? 18 and 72. Does that compare with the book? Okay. We got there. The arithmetic can get to you, but or the math can get a little complicated when you start dealing with multiple angles because of the why. Well, it gets confusing because there is a, the instant you take an inverse sine, you have to consider the range of the inverse function. And does it, so you have to, it's always going to give you an answer between 0 and, well, in the case of sine, it's going to be between minus pi over 2 and pi over 2. Or 270, or minus 90 degrees and plus 90 degrees. So when in a case like this, especially when you've got the fact that double angle snuck in on you, pushed you past that 90 degree point, so there's a second angle out there that you have to find. Everybody got this? Any questions, comments? All right. And that went the first half of the class. So I'm going to give you somebody asked about number 36. I'm going to tell you this. If you solve, there's no numbers given, so there's no calculations or arithmetic. It's strictly the math. But if you solve the equation of motion for when the water balloon reaches the ground and when the boy reaches the ground, you find out that both of them are the same equation. Right? Now, let's get started on this week's material. How many of you are worried now that I haven't handed out an exam? Okay. I've got it right here. You're welcome to have it. I will pass them out right now for you, in fact. These are take-home exams. So, and I grabbed the wrong folder. Here we go. Here are your take-home exams. Bring them back Wednesday to class. For you, this does not mean you get to leave early. We're still covering Newton's laws. Who can tell me what Newton's laws of motion are? Yeah, very good. That's one of them. Can you tell me which one? No. Can you tell me the other two? Well, how about I tell you that? Thank you, Nate. There's three of them. Actually, that one is about universal gravitation, which all derives out of this. That's one of them too. Let's see. Object at rest will remain at rest, and object in motion will remain in motion unless acted upon by an outside force. I'm trying to think and walk at the same time, so. Yeah, here. It is force equals mass times acceleration. First law of motion. Every object continues in its state of rest or uniform motion in a straight line until acted upon by an outside force. Second law of motion is the equation. The vector sum of the forces acting upon a body equals the mass of the body times the acceleration it experiences. And the third law of motion is that every action has an equal and opposite reaction. Whatever force is acted upon a body, the body acts. When one object exerts a force against another body, then the other body also exerts an equal and opposite force against the first body. Those are the three motions, or the three laws of motion. Let's start with the idea of force. What is force? It's the application of changing the inertial state of a body or an object. It's, mathematically it's easy to define. It's mass times acceleration. Intuitively, force is how you change, it's how you produce acceleration. It's how you change the velocity of another object, which is what mass times acceleration means. But intuitively, we all understand forces. We can feel forces. We can exert forces. But the first one, this is Newton's first law of motion. An object at rest will remain at rest and an object in motion will remain in motion until and unless acted upon by an outside force. That's the famous, commonly heard phrasing of Newton's first law of motion. There are variations of it. Sometimes you'll read where it says the object will continue in motion in a straight line until acted upon it by an outside force. Or an object with, the simplest statement of it might be to simply state that the velocity of an object will remain constant unless acted upon by an outside force. And recognizing that 0 meters per second is a velocity. And if the velocity is, since the velocity is a vector, any change in that vector, which includes any change in direction, would also constitute an acceleration and would therefore require a force. There are different ways you can phrase the same thing, but they all come down to the idea of inertia. And that is, in fact, this is, frankly, about the best definition of inertia you're going to find, is that velocity will remain constant unless acted upon by an outside force. If velocity is 0, it will stay 0. If velocity is so many meters per second, it will remain that many meters per second, and it will continue in that direction until and unless an outside force acts upon it. So that brings up the big question, and this really is one of the big physics questions that has haunted scientists for millennia. What is inertia? Go around the room, take turns. Give me your best, off the cuff, in your own words, explanation of what do I mean when I say inertia? Saul, you're up. Don't anybody else get smug because I'm coming around the room, so start thinking now. Go ahead, Saul, you're doing a good, you're just buying them some time so that you're the one in the hot seat. Say again? Inertia is something that, no, a force would move an object, but, and this is, you're getting an idea of the struggle, though. What is inertia? Alexia. No, I don't have a Siri either. I don't bug my own house. I'm certainly not going to let Amazon or Apple do it. Just off the top of your head, how would you explain the concept of inertia? Okay. Believe it or not, that's not a bad answer at all. Oh, I'll get there. That really is not a bad answer. It's, in fact, it's one of Heber's aphorisms. Is that, the hardest part of being right all the time is learning that I don't know is usually the right answer. Tyler. Yeah, you did. Too late now. You can't take it back. No take backs. Momentum is physically, momentum is just a really incredibly important property that we're going to get to later on in the semester. And it's a very well-defined physical quantity. Say again? Yeah. But what is it? That's your answer. I'm pretty sure that's everybody else's answer too, now that somebody's Googled it. The short answer is, quote Alexia, not Alexis. The short answer is, we don't know. We don't know what inertia is. We don't know what causes it. We don't know why it works the way it does. We can't mathematically describe it. All we can tell you is that inertia is a property of matter. And it is the tendency of matter to maintain a constant velocity, which is a roundabout way of saying red is the color that is red in color. Not a very good definition at all, but it is the best description or explanation of what we mean by the word that we can come up with. It is a property of matter. Now, what is the measure of matter? And by matter, I don't mean importance. I mean physical substance. What is the measure of matter? Mass, exactly. Mass is the measure of matter. It's the measure of how much matter do you have? How much matter are you talking about? One of the very first labs we did was density, which was mass per unit volume. Okay? And then that goes to the old joke about which is heavier, a pound of lead or a pound of feathers. Well, they're both going to weigh a pound. But the feathers are going to take up a whole lot more space. Mass is the measure of matter, and matter has a property that we call inertia. It means that whatever matter is, which is a whole nother question in and of itself, whatever matter is, it has this property that we call inertia, that its velocity will remain constant unless something else acts upon it and exerts a force on it. That is Newton's first law of motion. I think we talked about the units of mass. Kilograms. Does anyone remember what I told you was the unit of mass in the English system? You know, SAE, American. Slugs, exactly. Pounds is not a unit of mass. Pound is a unit of weight, of force. What would the metric equivalent of force be? Of pounds? No, kilograms are mass. Kilograms would be the metric equivalent of a slug, a Newton. Mass times acceleration. Kilograms, meters per second squared. So, that's Newton's first law. Matter is measured in units of mass. If you have 2.2 kilograms of, is it 2.2 kilograms? No, it's 2.2 pounds is 1 kilogram. Yeah, I think that's right. Google it and make sure. If you have 2.2 pounds of something on Earth, you have 1 kilogram of that thing. How many of you have ever heard of, who can tell me what a ton is? 2,000 pounds. What's a metric ton? What's the difference between a metric ton and a normal ton? Or an SAE ton? 200 pounds, because a metric ton is 1,000 kilograms, which is, on Earth, would be 2,200 pounds, a little over. So the difference between a metric ton and a regular ton is 200 pounds. The metric ton is 200 pounds heavier, right? No, lighter. Don't trust me to do arithmetic in my head. Okay, if you go to the moon, we bring a metric ton of something to the moon, 1 kilogram of stuff to the moon, 1,000 kilograms of matter to the moon, where gravity is 1/6 what it is here. How much mass do we have when we get there? We still have the same 1,000 kilograms of mass. It will weigh 1/6 as much, but it will still be the same mass. That is a trick question that I think you're going to run into it in your homework assignments. When they ask how much does mass change from one environment to another, from one planet to another, if you go into the weightlessness of space, you still have the same amount of mass, even though there's no weight. It weighs nothing. The mass is the same, which means if you're floating along inside a spaceship between the Earth and the moon, going to land on the moon, or you're going to Mars and you're in the weightlessness of space, and you've got 1,000 kilogram block of whatever you're bringing with you, if you try to push on it, you're going to have to exert the same amount of force to get it moving, even though it's weightless, because the matter still has the same property of inertia. Now, that brings up one more topic I want to start talking about today, and we're going to finish. We're going to go through several more of this over Wednesday and Friday. And that is the idea of an inertial reference frame. We've talked about relativity in that we've talked about relative motion. You know, if a train is going how fast relative to the ground, and another train is going that same speed, the opposite direction relative to the ground, how fast are they going relative to each other, etc. That boat is moving at 5 meters per second across the river's flowing at 3 meters per second that way. What's the net velocity of the boat? That's all relative. Well, Newton's laws of motion are going to introduce the idea of inertial reference frames. And I guess about the best way to define an inertial reference frame is a frame of reference in which Newton's inertial law, the first law of motion, holds true. It does not always hold true. This is not a universal constant. It is only true in inertial reference frames. What would be a non-inertial reference frame? A non-inertial reference frame is a frame that is not moving at a constant velocity. It's an accelerated reference frame is a good example of a non-inertial reference frame. And to make the point plain and intuitive to you, imagine that you're sitting in the passenger seat of your bud's car, and you put that giant 32-ounce icy or slushy or whatever on the dashboard. As long as y'all are traveling down the interstate, it sits right there, no problem. What happens when your friend turns the car too quickly? Hits the brakes, accelerates too fast. Does that cup does it remain motionless at rest on the dashboard, or does it find its way straight to your lap? Even though no force acted upon it, it still fell right straight into your lap because it had inertia. Newton's law of it wanting to stay at rest in that reference frame only applied as long as that reference frame was inertial, moving at a constant velocity. The instant that that reference frame accelerated, whether that was to brake, to turn, to speed up, Newton's law of motion no longer applied. That's why this is also referred to as Newton's law of inertia, his first law of motion. And I'm out of time, so bring your exam back on Wednesday. And anybody that has their homework can turn it in now. Anybody that doesn't have your homework, get it done and turn it in. We're running out of semester for me to start getting backlogged with things to grade. Thank you, John. Thank you, love. Thank you, love.